So in the periodic table, we studied the properties of elements. The properties are, first, the atomic size or the atomic radius. Second, the ionization energy. In the atomic size, we also studied the ionic radius, and we proved that the radius of the anion is greater than the radius of the corresponding atom, and the radius of the cation is less than the radius of the corresponding atom. In the ionization energy, we are interested only by the first IE, the first ionization energy, which is the energy absorbed by the atom to remove the first electron. But we studied also the second and the third ionization energy, and we proved that in general, I1 or IE1 is less than IE2, is less than IE3, is less than IEN. That means the first electron extracted is the easiest. Then we studied the trends in the periodic table. What is the meaning of the trends? If you have elements, you put your elements in the periodic table according to their places. So according to the group or period, to the row or the column, you can compare qualitatively these trends. The atomic size and the ionization energy depends on the type of attraction between the nucleus and the outer electron. As attraction increase, the radius decrease, the ionization energy increase. And the atomic size in the periodic table increase from right to left to down with no exceptions. And the ionization energy increase in the opposite order, from down to up, from left to right, but in the same row, in the same line, in the same period, we have exception between the group 2 and the group 3 due to the presence of the single electron in group 3, and between 5 and 6 due to the high stability of the orbital half-filled of group 5. The third property to be studied is the electron affinity, noted EA or simply E dot A. What is the electron affinity? If the ionization energy, the definition of the ionization energy is the energy absorbed by the atom to remove one electron from its valence shell, the electron affinity is the energy to add electron to an atom at the gas state. So if we have M gas plus 1 electron, that gives Fm minus gas. The energy of this process is called the electron affinity. The ionization energy is always positive. The electron affinity may be positive or negative depending on the distribution of the electrons on this atom. Suppose you enter to the classroom, the first probability is that you find directly your place in a certain row. Suppose, for example, you have one vacant place in row 1, so you can enter to the classroom and occupy directly this row. So the number of students on the row will increase, and the interaction between the students will increase, so we will have excess of the energy that will be released. That means if the student enters the classroom and can find directly his place, so the electron affinity is exothermic, and in this case, the electron affinity is negative. Suppose the other case, the student enters to the classroom and did not find his place on row 1, so he has to pass to row 2. And according to Bohr theory, when we pass from a lower energy level to higher energy level, the atom should absorb energy. So in this case, if the student did not find his place, he has to pass to higher level and the classroom will absorb energy. So in this case, the electron affinity is positive, is endothermic. So the electron affinity can be exothermic if the electron finds directly its place. For example, in case of sulfur, the electron configuration ends by s2p4. So P can receive another 2 electrons. If the electron is added, it will find directly its place on P4. So in this case, the electron affinity is exothermic. If we, for example, the rare gas, their electronic configuration ends by s2p6. So the level is completely filled and no places for electron to be added. In this case, the electron should pass to other higher orbital, and the electron affinity is in this case endothermic. So the electron affinity exothermic negative or endothermic positive depends on the electronic configuration of the element where we want to add this electron. So the noble gas that have valence shell completely filled will have positive electron affinity since no direct place at the level. It should pass to higher level. 1s2, 2s2, 2p6 is the electron configuration of neon 10. So the electron added could not occupy to p6 since this level is completely filled. It passed to higher energy, so the electron affinity is positive. As a general rule, the more energy that is released, the larger the electron affinity of the atom. The more energy that is released, the larger electron affinity of the atom. So the more negative value means the larger electron affinity. This is a general rule. In the electron affinity, we have a lot of exceptions, as in the case of the ionization energy. But we will not study these exceptions. We will follow only this rule: the more negative the value of EA means the larger electron affinity. So if we look, for example, to the periodic table, we observe that for some elements, the electron affinity is negative. For others, the electron affinity is positive. Consider one exception or one example, which is the nitrogen. The nitrogen ends by P3. And if we want to add electron to nitrogen, by theory, this electron could be added to P3 orbital. Since P3 is not completely filled, it can receive 3 more electrons. But as described or studied before, that the P3 is an orbital, very stable, so the electron added to nitrogen could not occupy the P3 due to the stability of this orbital, since it's half-filled. In this case, the electron will pass to higher level, so the electron affinity of nitrogen will be positive. So this is an example of the exceptions. What is the trend of the electron affinity in the periodic table? The electron affinity increase down the column, so from up to down, and increase across the period with lot of exceptions. Okay, so we have lot of exceptions. We will consider only the general trend.